Welcome, everyone. Today, we are exploring a watershed moment in cybersecurity. We are going to unpack exactly how Anthropic's Claude Mythos model uncovered a 16-year-old critical flaw in FFmpeg bug that survived millions of tests and decades of human review. Let's get started. Let's begin by setting the stage. In April 2026, the cybersecurity world experienced a massive shock. Anthropic announced that their new frontier model, Claude Mythos, had autonomously found a 16-year-old zero-day vulnerability in FFmpeg. FFmpeg is the backbone of almost all video processing on the internet. What makes this so profound is how the bug was found. The AI wasn't trained specifically on this exploit, it was simply placed in a secure container with the FFmpeg source code and asked to find a vulnerability. It read the code, theorized a weakness, and successfully identified a logic gap that was introduced all the way back in 2003. This event marks the definitive shift from human speed bug hunting to machine speed vulnerability discovery. Looking at this timeline, we can see the life cycle of this specific vulnerability. It originated with a benign code commit in 2003. A seemingly harmless refactoring in 2010 inadvertently turned it into a vulnerability. For the next 16 years, the bug remained hidden in plain sight, completely undetected by the global open-source community, until Claude Mythos finally exposed it in 2026. Why did it take 16 years to find this? To understand that, we need to look at traditional testing. The industry standard for testing media libraries like FFmpeg is called fuzzing. Fuzzing involves throwing millions of randomly generated video files at the software to see if it crashes. FFmpeg is one of the most fuzzed projects on Earth. Automated tools hit this exact vulnerable code path 5 million times without ever triggering an error. Fuzzing failed because it is mathematically blind. It relies on random chance to hit a broken state. Claude Mythos, however, uses deep semantic reasoning. It doesn't guess. It reads the C source code, understands what the human developer was trying to achieve, and mathematically calculates the exact edge case scenario required to break the logic. This flowchart contrasts the two security testing paradigms. On the left, traditional fuzzing relies on millions of random inputs. Because it lacks context, it misses highly specific logic flaws, leaving the bug hidden for 16 years. On the right, AI semantic reasoning reads the source code's intent. It bypasses the need for random guessing and directly calculates the exact exploit path, finding the zero day in a matter of hours. Let's dive into the actual code flaw. The vulnerability lives in the widely used H.264 codec. In H.264, video frames are broken down into slices, and the software uses a tracking table to remember which slice owns which block of pixels. Here is the critical mistake. The developers made the master slice counter a 32-bit integer, but the tracking table only used 16-bit integers. To set the table to empty at the start, they used a standard C programming command, memsetTable -1. In computer memory, a -1 fills the bytes with all ones, or hexFF. For a 16-bit unsigned integer, that translates to the maximum value of 65,535. The developers essentially said, if the table says 65535, treat it as an empty slot. This sentinel value assumption is the trap the developers set for themselves. This diagram illustrates the architecture mismatch. We have a 32-bit slice counter capable of massive numbers, pushing data into a 16-bit tracking table that maxes out at 65,535. The initialization step, using memset -1, explicitly sets the table cells to 65535, establishing it as the sentinel value for empty. This creates a dangerous mathematical ceiling. How do you exploit this mismatch? Mythos realized it could weaponize that sentinel value through a forced collision. Under normal, everyday circumstances, a video file only uses a few slices per frame, meaning that 16-bit limit of 65,535 is never naturally reached. That's why random fuzzing missed it. Mythos took a different route. It autonomously engineered a malicious video frame packed with exactly 65,536 slices. Because computers start counting at 0, the very last slice in that frame is assigned the ID number 65,535. This is the stroke of genius. The attacker's valid slice ID now perfectly matches the system's hard-coded empty sentinel value. Human reviewers missed this for 16 years because it looks like normal logic, but the AI saw the mathematical overlap immediately. Follow the exploit logic here. The attacker injects a malicious video frame with exactly 65,536 slices, generating a final slice ID of 65,535. Simultaneously, the system relies on its sentinel value of 65,535 to mean empty. These two states crash into each other at the collision node, allowing a valid attacker-controlled slice to perfectly masquerade as the system's empty state. Let's look at the exact moment of failure. When FFmpeg decodes the video, it applies a deblocking filter. This filter constantly asks the system, is the pixel block to my left in the same slice as me? To answer, it checks the tracking table. The decoder looks at its own slice ID, which the attacker forced to be 65,535, and compares it against the table's padding entry, which is also 65535. The system gets a perfect match. It fatally concludes that a completely non-existent neighbor block is real and safe to interact with. Because it trusts this false reality, the software bypasses its safety boundaries and writes data out of bounds directly into heap memory. This immediately corrupts the system and crashes the process. A single integer collision completely defeats the software's security perimeter. This decision tree maps the fatal error. The decoder check initiates a comparison. It looks at its self ID of 65535 and the table ID of 65,535. The evaluation results in a false positive match. This forces the system to assume a non-existent neighbor is real, which drives the execution directly into an out-of-bounds memory write, resulting in a severe crash. You might think, okay, it crashes a video player, so what? In cybersecurity, an out-of-bounds memory write is the foundational building block for remote code execution. A crash is just a denial of service, but in the hands of an attacker, that corrupted memory can be hijacked to run malicious code. This is why Mythos is terrifying. It is an agentic hacker. It doesn't just flag the bug and stop, it autonomously writes the exploit. In other tests, Anthropic proved Mythos could chain minor memory bugs with OS logic flaws to completely bypass security sandboxes. For example, it used return-oriented programming to gain full, unauthenticated root access on a FreeBSD server. It takes these tiny, obscure memory overlaps and weaponizes them, shrinking the timeline of exploit development from human weeks down to machine minutes. This sequence diagram shows how an AI escalates a crash into a full compromise. The Mythos agent triggers the out-of-bounds write, which exposes the target's memory layout. The AI then dynamically chains a second bug to bypass memory randomization. Finally, it executes its payload, forcing the operating system to grant unauthenticated root access. The AI handles every step autonomously. Let's apply this to a real-time, critical use case, securing enterprise media pipelines. Imagine you run a major cloud video platform. Millions of users upload untrusted video files every day, and your servers use FFmpeg to transcode them. If an attacker uploads a video specifically crafted with 65,536 slices, it hits your server, triggers the vulnerability, and either crashes your entire transcoding farm or hijacks the server instance. To defend against this, enterprises must deploy cloud security posture management powered by defensive frontier AI. By running a defensive Mythos agent against your own repositories, the AI continuously scans open-source dependencies like FFmpeg. It identifies the logic flaw, simulates the attack, and generates a predictive patch before the hackers can weaponize it. You must use machine speed defense to neutralize machine speed attacks. Here is the architecture for a secured media pipeline. The untrusted user video upload hits an AI security gateway. The defensive Mythos scan analyzes the file's structure. If it detects malicious slice parameters, it blocks the upload, quarantines the file, and alerts the SOC to generate a patch. If the file is clean, it passes safely to the FFmpeg server for transcoding and delivery. To conclude, the 16-year blind spot in FFmpeg is a wake-up call. It proves that just because code is heavily tested by traditional tools does not mean it is secure against advanced AI reasoning. We are facing a vulnerability tsunami. As open-source AI models reach this level of capability, the volume of 0 days discovered globally will explode. You must adapt. You have to shift left at AI speed, integrating frontier models directly into your development lifecycle so you can break your own code before adversaries do. You must enforce zero trust, assuming all your software dependencies are already vulnerable. Human speed patching is obsolete. Automation is the only path forward. To master these cutting-edge cybersecurity strategies and safeguard your career, I invite you to like, subscribe, and visit quicktechie.com for premium certification prep. We offer comprehensive Q&A banks, full ebooks, audiobooks, full-length training, and expert interview guides. Secure your future with QuickTechie today. Our final diagram outlines the required AI-era security posture. To survive the coming vulnerability tsunami, you must embrace 4 pillars: automated patching, shift-left AI scans, zero-trust architecture, and an autonomous security operations center. Integrating these elements ensures your infrastructure remains resilient in a world where software vulnerabilities are discovered and exploited at machine speed.
To find related ebook and other material for this training course, go to quicktechie.com. Now you will see all the video courses are available here. So let's move to the ebooks. You can go here, ebooks, all AI related ebooks, like you are watching currently Mythos related training. That ebook would be uploaded under this section. You can download this ebook. PDF would be available, all 300-page PDF. So you just click on the download this entire ebook. You can download from this section. So whatever training you are currently listening, corresponding ebook would be available. We have thousands of ebooks available. Now, other than that, we have on video courses which you are watching right now. This also all AI related courses are available. Similarly, for all company related trainings are available, like Microsoft. You can find it here with their respective certification training modules. All exam simulators which would help you to get the certification preparation. Just refresh if you get this kind of error. Okay, so now you can see these are all certification preparation materials. Will also be click here to the NVIDIA certification preparation material. So you can see all NVIDIA certification preparation materials, and click on any of this and it would load the entire screen and you can launch the practice paper. So this is what you can see, that you can submit the answer. We have an audiobooks available. Okay, so for each section, and these are our alumni who can you can find out all alumni who are accessing our portal.